Welcome to our new video on the quantum mechanics on the Larmors Precession. So this is the quantum mechanical precession. I mean that we have studied the precession in the case of the classical physics, where we studied about the precession of a top. So just like this, in quantum mechanics, we have to study the precession of the electron who is spinning about its axis. So what's the precession? Just like in the case of top, you can imagine that there is an electron there, and how to calculate all of the spin mathematics of the electron we are going to discuss in this particular video. And also that what is the frequency of the precession of an electron when it's doing the precession. So how it's doing the precession? So it's doing precession when we apply the magnetic field in the z direction, and electron is also tilted at some particular angle from the z-axis, and it's spinning. So it's, as you can see that here in the diagram, you can see that it's making a cone. So you can imagine that the electron is also spinning, and it's also rotating about a particular angular frequency, and that we have to find out. And it's like a circular path, as you can see that in the case of it's making a cone like thing. So that is a precision or in the quantum mechanics. So we have to study all of the mathematics, which means we are going to study that how the spin in the x, y, and z direction are dependent upon time, or they are not dependent upon time. We are going to derive that. This is all about the basic introductions to the precession, and that precession of electron was called the Larmor's precession, and the corresponding frequency is called the Larmor frequency. We are not only going to discuss about the derivation of the frequency of the electron or of the angular frequency of that precession, but also whole mathematics about it, about the spin and all of its states, etc., etc. So let's start our today's video. So first of all, let's understand that particular diagram. So as we can see that in this particular diagram, there is a magnetic field in the k cap direction, which means in the z direction, and the arrows that I have made define that the magnetic field is in the this particular z direction. Alpha is the inclination of the particular axis of electron of that particular circle it's moving. So this is the alpha here. So let's start. First of all, we have to write some of the important definitions, and one of is the mu, which is called the magnetic dipole moment of an electron, and it's defined as gamma s, where gamma is the gyromagnetic ratio and s is the spin angular momentum of the electron. So this is how we are going to define the magnetic dipole moment. So how we are going to define the energy. So energy, you also have studied in the magnetism that the energy, which is the Hamiltonian in the case of the quantum mechanics, is defined as the magnetic dipole moment mu dot B, where B is the magnetic field, and in this case the magnetic field is B naught. Just like the classical one, the energy is minimum when the electron dipole moment is parallel to that of the magnetic field, where the energy is minimum. So here we have defined the Hamiltonian for our system. Now, as you can also see that the particle is spinning and it's not moving, it means we do not have to understand, and we do not have to take the position state of the particle. We only have to encounter the spin state of the particle. So let's see here what we can do. So first of all, substituting here as Hamiltonian is equals to gamma s b naught. So this is our Hamiltonian. So in this case, as we have imagined that the magnetic field is in the z direction, so the component of the spin that we are taking in this particular scenario is the z direction, which is gamma b naught s z. So this sz will be going to our the direction of the spin in this particular case. Now what we have to do is that we have to find out the how the spin in the x, y, and z direction are going to behave with respect to the time. They are time dependent or they are time independent. We are going to discuss in this particular video. So first of all, we have to solve the Schrodinger wave equation, and this Schrodinger wave equation is going to be the time dependent form, not the time independent form. That's why it's quite a little bit of complex. So first of all, let's write out the equations first. As you can see that Hamiltonian is described in this particular situation, and we can put down the value of these particular S shed. So if you have studied the spin states, the video on my spin state, you may know that what is the S jet. So S shed, which is spin in jet direction, is h bar divided by 2, and in the matrix notation, it's 1, 0, and 0 minus 1, 2 into 2 matrix. Okay, so this is the SZ spin. So as you can see that here, our Hamiltonian is there, and I have mentioned that here is we are not going to deal the position state of the particle. We are only going to describe the spin state of the particle, as particle is spinning, not moving. So it's quite easy. Okay, so this is our Hamiltonian, and this is our SZ. This is our the spin in the Z direction. So this is our Hamiltonian we have written. Now what we have to next do is that we have to find out the energy of this particular electron which is doing precession and it's spinning. So how we are going to do this? So if you have studied a little bit of the spin states in my video where I've discussed about this particular fact, that when you apply this particular SZ operator, because this SZ operator will, what you will give you in the spin state, let's say x plus. What is x plus? So x plus is the spin up. It is the state of the particle where the spin is up, which is the positive 1 by 2. So SZ, it will yield positive of h bar divided by 2 x plus. So this is an eigenvalue equation. What does this mean? This means that here, when we apply the SZ, where SZ is the correspondingly operator to find out the momentum, sorry, to find out the spin in the Z direction. When we apply this with the our spin state x plus, where x plus means the particle is spin up, then this is a result going to be in the Z direction. So just like this, when we apply this SZ operator, so I'm going to write out the SZ operator so you will not confuse that SZ operator is nothing, is h bar divided by 2, 1, 0, and 0, negative 1. So this is the SZ, this is the operator. So when we apply this particular operator to this x plus, not x plus, sorry, it's the spin state where the spin is up, you will get this particular value, and this particular value will represent the spin, that in which direction there is a spin of that particular particle. So just like this, when you do the same thing of this particular sign mean that the spin is spin down. So this is negative of h bar divided by 2 minus. So this is the second eigenvalue equation, and this is the correspondingly eigenvalue, and this eigenvalue will generally show you that what's the spin of that particular particle. Just like in the, you can conclude that you can join these two particular scenarios, like in the quantum mechanical systems of position state. When you are applying this particular x operator, it means for any of the observable, like the expectation value of the position, there's correspondingly an operator. So just like this, here in this case, for finding the spin in the z direction, there is an operator, and that operator is this. That operator is this. Are you combining these two particular facts, linking between the two particular facts? Just like this, if you have to measure the momentum in the case of the particle, what you will do? You will apply the momentum operator to the position state, and you will get the momentum of the particle. So just like this, here it's going on that what if you have to find out that what's the spin in the z direction, there is an operator corresponding to this. and that is this SZ operator. I hope you understand all of that stuff. Here our spin state is spin up and spin down. Sorry, here I think the sign is missing. Yeah, the sign is missing. Here the Hamiltonian energy is negative of the magnetic dipole moment dot B naught, so it will be negative and it will be negative. So here in this case, we do not have to deal with the position state. We have to deal with the spin state, and the spin state is x plus and x minus. So let's calculate the energy in this particular case. So you have Hamiltonian. So when you apply Hamiltonian just like this, for this particular x plus case, you will get the energy of plus energy in the spin up case and multiplied by this equation. So this is also the eigenvalue equation. So using this equation, you can find out the energy of the electron when the electron is the spin up, and correspondingly you can find out the Hamiltonian when the spin is spin down, and you will get that particular energy. This is the two correspondingly equations, eigenvalue equations of the Hamiltonian or the energy of this particular system. Okay, so now you have to calculate it. How you are going to calculate it? It's quite easy. How? So let's see here. If you apply the Hamiltonian operator, which is in our case it's negative of it's gamma B naught Sz, and you are applying this particular operator to the x plus, what you will get, it's easy. You have to see this particular result. When you apply this particular as z operator to our spin up state, you will get the positive of h bar by 2. It means what you are going to see here, I think I have 2 here. Okay. So what you are going to see here is that you will get the same b naught h bar divided by 2 and negative, and here is spin up. So this is our eigenvalue in this particular case, and this eigenvalue is what the energy when the particle is spin up, when the particle has the spin up. So this is our energy. So just like this is our first case. So when this particle is spin down, then you are going to apply this same B naught one minute. I guess two will not be here. You can remove the 2. Okay, so just like this, B naught, gamma B naught Sz. Now for the spin down states, it will result as the positive of gamma B naught H bar by 2, and here x minus. So this is our now energy. This is now our energy for the spin down state of the electron. So let's conclude that what we have found. So the Hamiltonian, which is the energy. So I'm gonna write it here. First of all, applying this Hamiltonian for the spin up case, you will get the energy for the particle, and this is an eigenvalue equation for sure. And this energy is negative gamma B naught H bar by 1 minute. Let's write it. E plus is negative of gamma B naught H bar by 2. So this is our first case. So just like this, for our second case, when we apply this Hamiltonian operator for the spin down state, it will result as the energy for the spin down state, which is represented by here the negative in our subscript, and it will positive of gamma b naught h bar by 2. Now we have done this calculations. Now we have to solve our Schrodinger wave equation for the time in dependent form. How we are going to do that? So if you have studied that we can write any of this particular, let's say you have a state, you have a wave function which is not dependent upon time. Let's say is psi1 x, and you have something. Let's imagine I am taking any of these particular values. You can, it's not the accurate value, but I'm just taking it to for a better understanding. So let's say we have wave function, first wave function for our time independent case, second wave function for our time independent case. Let's say it's a 1 minute. I'm just taking random values. Maybe the wave function that I have taken is not correct, but I'm just taking the random values. So just simplify that what I'm trying to say. So let's say it's a cos, okay, a cos omega t. Suppose that you have two wave functions which are independent upon time. So the theory of quantum mechanics says that you can write down the time dependent form as the linear combinations of these two particular states. What's the meaning of the linear combinations? Mean multiply with it some such sorts of constants. Let's say multiply c of psi 1x plus d of psi 2x. So this is what the linear combination says, that when you have some sort of wave function which is independent of time, and you want to find out the wave function that will be dependent upon time, then you can do this with the linear combinations of that particular time independent case. And this particular thing I'm going to use here. So let me erase this. So same, I'm going to use this particular fact. Okay, now we are going to solve out the wave equation. So just like we have deduced, now we are going to do this. First of all, what is the time dependent form? The time dependent form is x divided by del t, and this is equals to the Hamiltonian x. This is not x, okay? So please do not assume that this is x. This is the spin state. Okay, so I will not also say this particular thing x. So this is not x, this is the spin state. Okay, so why here I've written the spin state? Because there is not any type of the position state. That's why this is our spin state. I'm going to write it here in a very big words that this is a spin state, not the x. Okay, so this is our spin state. So iota h cut del by del t of our spin state is equals to Hamiltonian spin state. So just using this particular fact, I'm going to write out the spin state as the dependence upon time, as this is equals to the a, where a is the some sort of constants, which I have just discussed now, that when you have to take the linear combinations, you multiply with some sort of constants. A, and it is x plus and e to the power negative iota e plus, it's e plus t divided by h cut plus some sort of constants, let's say b, x minus e to the power negative iota e minus t divided by h cut. So this is the linear combinations, and these linear combinations will yield the time dependent form of our spin states. Okay, So first of all, we are going to substitute the values of energy, which is A spin up e to the power negative. What's the energy for the positive case? So for the energy of the positive case, it will become positive iota gamma b naught t. I think it will be b naught t divided by 2. And here the h cut and h cut will generally cut out. Plus b spin down e raised to the power, it will become positive and negative. It will remain negative I gamma b naught t, and h cut will cut out divided by 2. If you're confused that why I haven't here taken the h cut, then you can see that here for the energy case it is h bar. So you can just substitute h bar here, and h bar will cut out. So it will not point of view to write down this whole equations and all of that thing. I've just taken it straight for conclusions. So this is our time dependent form of the spin states. So let's write this particular scenario in the matrix form, because matrix form is very much helpful. So how are we going to write this in a matrix form? Quite easy. Here x plus, if you don't know that here, what's the x, not x, but what the spin up. So spin up is represented in the matrix form as 1 0, and the spin down is represented as 0 1. So these are the spin up and spin down states for the quantum mechanics, 1 0 and 0 1. That's the matrix formulation. That's why very much important, because it simplifies all of that particular problem. So what you have to do is that you have to put down the here matrix formulations of x plus and x minus. Sorry, again I'm saying x plus. Sorry for that. X not express the spin up and spin down. You will put down these matrix formulations of a spin up and spin down. And if you do the simple basic mathematics of the matrix notations, at the end, what you will find is that it will be in the matrix notation as A. This is positive sign. Yes, this is positive sign. Okay, A, E, iota, gamma, B naught, T divided by 2, and B, E, negative iota gamma b naught t divided by 2. Here, so this is the matrix formulations of the time dependent spin states. Now what we have to do is that here are two constants a and b. So how are you gonna find them? So this is your homework, that you have to find out the constants a and b. I'm giving you a hint that you have to put down the initial conditions by putting down the spin state time t is equals to 0, and using the equation mod of a square plus mod of b square is equals to 1. Okay, so you have to find out it. I'm going to write it, that what should be. So the value of A, which you will yield after this particular scenario, will be cos alpha by 2. Now you are seeing the significance of that particular alpha, where I have discussed that alpha is nothing, it's just the inclinations from the z and z axis of this particular spinning of this electron. Okay, so A will be this, and B will be sine alpha divided by 2. You have to find it, okay? I'm not gonna find it because it will just increase the length of the video. These are the basic things and you have to know, and you can derive it. Now the spin state of the particle. 1 minute, okay. Now the spin state of the particle can be written as putting down the value of A as cos alpha by 2 e to the power iota gamma b naught t divided by 2 and sine alpha divided by 2 e to the power negative iota gamma b naught t divided by 2. So this is our time-dependent case of the spin state. Now, what's our motive of this particular video? If you remember, the motive of this particular video is to understand that whether the spin in the x, y, and z directions are dependent upon time or not. So let's see how we are going to, I mean to say the expectation value of this particular x spin in the x, y, and z direction. So if you know that how we can find out the expectation value. So expectation value, let's now calculate it. The expectation value. So now this is our second part we will discuss. Okay, now we are going to discuss the expectation values, all that stuffs. Expectation values. Okay, so the expectation value for our x case can be written in this particular form. X of t complex conjugate Sx, and not x of t, the spin state's complex conjugate, and then here is a very good form of writing and finding out the expressions for our expectation value of x. Just like this, we can write this particular scenario for your y and z cases. So Sy expectation value, the spin state's complex conjugate of time dependent form, here Sy, and then again spin states. Here Sx and Sy are the corresponding operators, okay? And just same for the Sz case. So let's find out the values of the expectation values in the x direction. It's quite simple. You have to do the complex conjugate of this particular equation. And I'm pretty sure that you all must know that what exactly is the complex conjugate, because this is the full basics that how to do the complex conjugate in this particular scenario. So it will yield this particular value. It's equals to the cos alpha divided by 2 e to the power negative iota it will be, and gamma b naught t divided by 2. And here the complex conjugate will be the sine alpha divided by 2 e to the power negative, it will become the positive iota gamma b naught t divided by 2. So this will be the complex conjugate part of the matrix notations and multiplied by the Sx. What is Sx here? Now this is the point that if you haven't know the formula, then I'm going to write it here that Sx is nothing. This is the h bar divided by 2, and here in matrix notation is 0, 1, 1, 0. This is also the Pauli spin matrix. And what's here Sy? Because we have studied Sz, so Sy is also going to be, if I remember, it's h bar divided by 2. I guess here it will be okay. Formula is 0, iota, negative iota, 0. So this is for our y case. So I'm calculating it for the x case here. So I have to put down this particular Sx here, which will h bar divided by 2, 0, 1, 1, 0. And again, you have to write down the spin states, which is cos alpha divided by 2. 1 minute. Cos alpha divided by 2 e to the power negative negative. No, in this case, it will not be negative because we are not taking the complex conjugate of this particular part. I gamma b naught t divided by 2. And here it will be sine alpha divided by 2. And it will be 1 minute. E raised to the power negative of iota gamma b naught t divided by 2. Okay, so now you have to just calculate this particular all of the stuffs. This is quite complex, so it's upon you, that it's the homework that you have to do this particular all of that stuffs. And I'm only taking the account of the final values that you will got, because if I'm going to do this, if I will do, then the video it will be very much long and I don't want it to be. So the final value that you will get after doing all of this particular calculation for your Sx expectation value is the h bar divided by 2 sine alpha cos gamma b naught magnetic field into the t. So as you can see here, the spin state in the x, the expectation value of the in the x direction of a spin is dependent upon time. So just like this, when you will do the calculation for the sy state, you will see that for the sy state, it is h bar divided by 2. This is h bar sine alpha, and again sine gamma b naught t. So this is first for our expectation value in the x case, and expectation value in the y case is also dependent upon time. But when you do the calculation, this same calculation for the sz case, then it's different, because you will get to know that it's independent upon time. It means expectation value in the z of the spin is equals to h bar divided by 2 and cos alpha. What is this? This means that it's a constant, because alpha here is a constant angle. So it means the expectation value is constant in the z direction. But in y and x direction, it's dependent upon time in this particular case. But finally, what's the frequency at which the electron is doing all of that particular precession? So the frequency of that precession, that's the angular frequency of that particular precession, is gamma. B naught. So this is the angular frequency. And using this particular formula, which is omega is 2 pi into frequency. Omega means the angular frequency is equals to 2 pi into the frequency. You will calculate the frequency for this particular precession. This is the angular frequency. So this is all about the spin states and all of the mathematics of the spin, that how the precession, the expectation value in the x, y, and z direction are dependent and independent upon time. As you can see that in the z direction, the expectation value is constant. It does not depend upon time, but in other cases, it depends upon time and all that thing. So this is my video on the on this all about the Larmor's frequency. I hope that you all understood this particular Larmor precession and the quantum mechanics. And the next video is also going to be on some sorts of experiment in the quantum mechanics. This Larmor precision is also some sort of experiment. Just like this, there is also one more experiment, and that particular experiment is the Stern-Gerlach experiment. So this is also very important. So maybe the next video is going to be on this particular topic. So for now, if you have any of the particular doubts, you can ask in the comment section. So I will be happy to solve all of that particular doubts. And if you find any some sort of mistakes in my this particular video, you can write down in the comment section. So thank you for watching my video.